And if there is a mistake done, so the grading person will take off some portion of the total credit. So it's not right or wrong, it's partially right, partially wrong, partial credit. So depending on how severe the mistake is, you may lose more or less points on the same problem, or maybe not at all, if it's just something really, really like simple. So because it's 2-hour exam on average, it gives you, well, if it's 8-problem exam, 15 minutes per problem, which is supposed to be way more than a prepared person may need, based on statistics from 11 years of this course. Did you have a question? Yes, please. I don't know what the study guide for the exam. In order to be prepared for the exam, you have to be preparing, which requires some certain work. But first I want to ask you a question. What does an instructor do? Please tell me. No, just answer the question, whatever comes to mind. What does an instructor do? Exactly. And what does an instructor use for that? Words. I can't do it this way. I don't have telepathic properties, abilities. So in order to understand instructions, first we need to understand the meaning of each individual word, right? For example, stol, ekran, мяч. What did I say? Stol, ekran, мяч. Better? Of course, when we speak the same language, it helps. A table, a screen, a ball. The next stage of understanding is understanding sentences. But then the next stage is understanding the meaning of those sentences. Not always the same thing, because otherwise people wouldn't say, look, man, I hear you, but I have no idea what you're saying. Oh, that's what you meant. Okay, I got it now. Instructions represent a list of actions. What to do, in which order, when, why. And when we understand those instructions, next step is trying them out, and the next step is practicing. And the standard course setting requires this should be done in the lecture. The rest should be happening outside of the classroom. And the best way to practice is, well, to practice. And that means doing something above the sheer requirement, above what was prescribed. Maybe not much, but still. How do we do that? Well, different people do it differently. Here I cannot give you an advice. But that's how you prepared for the exam. Well, we talk about vectors. A vector is an arrow. Yeah, we can describe a vector by its length or angle, by components. Components also have different meaning. vector components or number components or coordinates? Yes. You didn't check the Blackboard yet. Your question tells me you didn't check the Blackboard. It's a week in the course, and you didn't check the Blackboard. Because if you would check the Blackboard, you would find the equation sheets. They will be provided. You don't have to print it out. But they don't cover all possible equations, all the most important. So it's a saving time technique to memorize as many equations as possible, because in that case, you wouldn't be spending time on trying to recover. Yes? Oh, okay. Sorry, in that case. Yes, you will be able to use those equation sheets. Why would they be posted otherwise? Well, if you need to know what to memorize, go to Lecture 1 or to syllabus. Last 6 pages of the syllabus tells you what you need to memorize, ideally. Yes? Oh, not a question. All right. Just a motion. I'm like a frog. I see the motion. All right. So now I got to be honest with you. Last week, intentionally, I used the sloppy version of the language we have to use. When I was saying velocity is positive, velocity is negative, acceleration is positive, acceleration is negative, what I should have said is the x component of velocity is positive, the x component of velocity is negative, or the x component of acceleration is positive, or the x component of acceleration is negative. But at the time, we didn't know what component is, so I could not use that word. Now we know what a component is, so now we can use the accurate language, which happens in science every time. First, we establish the language which is not very accurate but sufficient to understand what's happening. Then we refine it, and again, so nothing new. Please now tell me what you think. Right now, you have to turn on the switch in your brain from monotasking to multitasking. Because right now you have to do many different tasks. You have to read. You have to keep listening to me, because who knows, maybe I'm saying something important. Maybe not, but you don't know. Now, you have to draw a picture. You have to choose your answer. You have to enter that answer. Yeah? So good thing our brain has parts. At least we can designate one half for listening and second half for watching, right? So a number plane has 4 quarters, and we call them quadrants. First quarter, second quarter, third quarter, fourth quarter, or if we use scientific language, first quadrant, second quadrant, third quadrant, fourth quadrant. And when we draw an arrow which satisfies those conditions, you could look at your picture and choose the answer. So first, of course, I always want to draw my own picture, because I don't trust anybody except myself. Now, if I know what to do, I just do it. If I don't know what to do, I use 100-old scientific method, trial and error. I try. All right. In this situation, I only have to try 4 options and see which works. This is the first option. Now I need to check for this arrow. What components would I have? Well, this would have been x component. Well, let's call it A. That would have been the y component. The x component would have been positive because it points in the positive x direction. The y component would have been positive because it points in positive y direction. But my components are negative, actually both. So what does it mean? Wrong. So what? This actually gives me a hint. All I have to do is flip it. Because if I have two positive components in my example, I need two negative components in the actual vector. I just have to flip the whole vector. Flipping means something like this. Now, because I can count counterclockwise, I count first quadrant, second quadrant, third quadrant. But of course, we can do much more. We can calculate the magnitude. We can calculate the directional angle for this vector. So all I have to do is just keep using my knowledge about vectors and components. So for example, if I draw two perpendiculars which automatically parallel to other axes, this is the x-axis, this is the y-axis. This arrow represents the y component, and the actual value of this y component should be equal to x component, negative 12. And this arrow should represent the y component, and the actual value, the coordinate, is negative 16. So what I have together with a vector, a right angle triangle, and when I do a triangle, I write length for each side. And this is my hypotenuse, so all I have to do is just apply a Pythagorean theorem. Done. Now about the angle. Unless we told something opposite, the angle, according to a definition, has to be measured from positive x direction toward the vector. This is the angle which mathematically describes the vector. But we can see this angle will be equal to 180 plus the internal angle in this triangle. We can see it. So all we have to do now is just calculate this angle alpha. We can use sine, cosine, tangent. I prefer tangent. I don't know why. I just like it. So tangent of this angle should be equal to the ratio. And of course, if I don't want to think, I have just two options, 12 over 16 or 16 over 12. One is wrong, one is correct. Yeah? Which is correct? Is this correct or this? The second one is correct. The second one is correct, exactly, opposite over adjacent, so this is wrong. And now alpha will be inversed tangent of this ratio. Done. Any questions? And you need to know your calculator, how it works, so you wouldn't be thinking about how calculating this on your calculator. Well, we talked about vector addition in general, so this is a quick review. We have to use a tail to a head rule to add vectors geometrically, or we can use components. For each vector, we have to calculate x and y component, add them up together. That gives components of a resultant, and done. Well, of course, we got to do an example. So these are two vectors. According to the strategy, we need to calculate the x component of A, the y component of A, the x component of B, the y component of B. Then we have to add them up all together. That gives the x component of the resultant, and this gives the y component of the resultant. So, but first, we always have to draw a picture. So first I want to draw a copy of A. It must have exactly the same direction and exactly the same magnitude. Then I have to draw a copy of B. And I have to do it according to a tail to a head rule. So the tail and the head will be placed together. That's only first step. Yeah. Move. Now we have to connect. So we have to complete it to a triangle. And we have to choose a direction. And to choose a direction, we have to imagine that each arrow represents certain displacement. A person walks like this and like this. That will be the start of the whole motion. That will be the end of the whole motion. So the resultant are points from start to finish. We can see it's almost vertical, so we can expect a very long y component for the resultant and a very short x component for the resultant. Well, now we just have to do it. Well, I have to complete the triangle. This is AX, AY. AX will be equal to hypotenuse 27.5 times cosine of 66. AY will be equal to hypotenuse 27.5 times the sine of 66. And I shouldn't spend any time on thinking about it. That should be automatically done. BX. Okay, components. Well, first of all, inside the triangle, I have to use this angle. So I have to use a geometry to figure out the value of this angle. Please, anybody, tell me the value of this angle. Cannot hear you. How did you find it? 180 minus. We have to use that knowledge about the whole angle. So it's 180 minus 12, 80 minus 12, 68. So now we can start writing the hypotenuse 30 times cosine of 68, the hypotenuse 30 times sine of 68. Now you see on the screen 4 numbers. 3 are correct, 1 is wrong. Please find and tell me which is wrong and how to fix it. Yes? Why? Absolutely correct. Nothing tricky about it. We need to know the rules and follow the rules. When a component points opposite to positive direction, it must be negative. Out of these components, 1, 2, 3, 4, 1 bx points opposite to positive x direction. So it must be negative, fixed. Now we just have to add them together. And please do it. Calculate and tell me the numbers. I wish I had extra credits for you, but I don't. But if I had, whoever would say something first would get some. Now all I can give you is just respect. Bless you. So please, anybody? the x component of the resultant are x. Anyone? Please. What's your number?
Negative for Rx is negative.
So why did you wait? I got exactly the same number. And what's your number for y?
52.13.
We can round it up. Well, that was the most important part of the calculation, because now, well, you see, this is practically 0. So in this example, the angle will be practically 90 degrees, and the magnitude will be practically 52, 53, something like that. In general, we would have to use, again, Pythagorean theorem, tangent, to get those numbers. Any questions, please? All right. Now, the exactly same reasoning can be used for any number of vectors. Doesn't have to be 2. Yeah. When we add in vectors, the rules which we used for numbers still can be used. Yeah. We can rearrange. The order doesn't matter. So basically, to add any number of vectors, we just have to add certain number of components. That's it. Now, we also need to learn how to subtract vectors, and for that we have to give a definition of a vector opposite to the given one. And this is a definition. A vector which is opposite to a given vector is a vector which has exactly the same magnitude but opposite direction. Very easy to remember. That's why we call it opposite. But the property of the opposite vector is very convenient. If you add the original vector and the opposite, the result is 0. Like with numbers, 5 plus negative 5 equals 0. They cancel each other out. And now we can use this to give a definition of subtraction. If we want to subtract a vector, we just have to add a vector opposite to the one we're subtracting. That's the definition. Now we got to do an example. So please do an example. Tell me what you think. If you would have to subtract the same vectors, a minus b would point. And these are the choices. How would it point? Oops. So you have to follow the definition, which is on the screen. A minus b is literally equal to a plus opposite b. Now you have to follow the definition what opposite means. Opposite means same magnitude, opposite direction. So you have to start from drawing your vectors. A minus b literally equals a plus negative b, which is a plus opposite b. So I just provided you instructions how to subtract vectors. You just have to finish the procedure, because we have converted subtraction into the addition. What do we know about vector addition? everything. So you have to apply that knowledge and choose your answer. And that's the question number 3. Survey says one is the most popular and also correct. Yeah. So all we have to do is just finish the procedure. This, a tail to a head, and now connect. And of course, we can use the component method to calculate the components of the resultant. Now we can see the R, the resultant, will be almost horizontal, so very short vertical component, very long horizontal component, and we can use the same numbers because we use the same vectors. So we just have to do it slightly differently mathematically. Now we have to subtract Rx will be equal to 11.2 minus negative 11.24. Minus makes it plus. So, well, 23-ish. And here, Ry will be equal to 25.1 minus 27.8. So it's going to be negative 2.7, negative 3, whatever. Now we know components. When we know components, we can finish calculation. We can calculate the magnitude. This is what we do in the end. X, Y. So the X component is long, 23, Rx. The Y component is short and negative, Ry. So the whole vector looks like this. We can calculate angle, we can calculate magnitude, and I think it's been done. Something like that, yeah. The last part has nothing to do to physics. So, well, now we're going to talk about projectile motion. Projectile motion happening when we have an object released from rest, but also give certain horizontal component of velocity. Well, and just keep it there. So, as you can see, there are many practical applications. Fireworks. We're going to do lots of stuff like that. No, we're not. I want to start from a question. What do you think, based on your everyday experience, about the trajectory of an object which was horizontally launched? Not like this, but like this. Rolls horizontally, and when gets off the table, its velocity initially was pointing to the left relative to you, but then it was falling down, but at the same time keep traveling along the ground. And this is how, well, I don't know, LeBron James, when shoots three-pointers, how he knows how to shoot? He calculates the angle, the initial speed, based on the distance from the ball to the hoop. Great mathematician. Let's see what you say. Well, he does it without knowing that his brain, our brain, is the most powerful computer to date. 2 wins. Okay. And 2, of course, is correct, because as long as an object is not touching, well, a table or a barrel, the force of gravity starts immediately acting on it and changing its direction, but it doesn't happen so the trajectory is not just tilted, trajectory is bent. And the same trajectory we would observe for any situation when an object was initially moving horizontally and then was released and falling on the ground. Well, in this situation, I don't know, a bowling ball was accidentally, what were they doing? I don't know. Of course, this problem is not about bowling ball. This problem is about bombing. That's how they calculate where it lands. But the physics is exactly the same, no matter how the projectile was launched. Now we're going to look at these 2 objects at the same time. So I'm going to prepare the demonstration first to explain what will be happening. Here I have a device which I can use to release the ball from rest. If it's released from rest, it just free falling down and hits. But I can use the same device to launch the ball horizontally. When it's launched horizontally, it falls according to trajectory number 2 and hits the ground. And when they both launched simultaneously, what might happen? Well, again, every time when we ask what might happen, first we have to list all possible options and then see which is going to work. Options. This hits first, this hits second. Second option, and the third option, that's all. And the question to you is about what do you think will happen in this experiment. So you should choose your answer and enter it, and we will be able to test it experimentally. But of course, looking at 2 balls simultaneously is very hard. So instead, you should rely on your hearing, because you can hear the difference. It's either or. That's it. Everybody has to enter the answer of your choice, which will A means this, B means that. If you think the ball A hits first, choose 2. If you think, come on in, or not, ball B hits first, choose 3. If you think they hit the table simultaneously, choose 4. If you think something else, choose something else. That's it. Did you enter? What did you enter? 4. Okay. You were right. Now, this is a very simple demonstration, but it gives a very important information about the projectile motion. The fact that the second ball was traveling horizontally, in addition to falling down, didn't affect the way it was falling down. So horizontal motion and vertical motion do not interfere, they do not interact, they happen independently, which means we can consider them, analyze them absolutely independently. When we talk about how fast it's falling, we can forget that it travels horizontally. When we talk about how it travels horizontally, we can forget that it's falling. That's very important. Before we go to mathematics, there's one more question I want to ask you. So, suppose you're driving, well, you can read, so please read. When I read this problem, every time I have exactly the same question. Are you crazy? You already have a convertible and probably an expensive rifle. Why would you do such a thing? Thrill, yeah. Get bored. Well, of course, we're not going to do this exact experiment, but we have a similar one. A similar experiment requires just a cart instead of a car and a launcher instead of a rifle. And I need a track to make sure the surface is leveled, because if it's not leveled, it's not going to work. No. Does it work? Okay, the launcher works. Now, I need to make sure that it shoots the ball straight up, not at any angle. So I have to check how it shoots, and when it checks, don't look inside. More or less, okay. Now, we're just going to charge it and give it a push. That's it. So if you said in front of you're wrong, behind you're wrong, it should come back exactly in, well, in the barrel of the rifle if you do the original experiment, or just in the launcher, back in the launcher. And the speed doesn't matter. The speed only affects how fast it travels relative to the ground horizontally. It doesn't affect the vertical motion. The speed, of course, might affect the distance between the place where it was launched and the place where it caught again. So we have to figure out how to calculate that distance, how to calculate the time it takes to travel up or down, etc., etc. And to do that, all we have to say is that the horizontal motion and the vertical motion do not interfere. So this, what would have happened in that crazy experiment? In order to make a transition to mathematical description, we have to say something mathematical about this vector. This vector represents a free fall acceleration. We know that a free fall is a motion of an object released falling freely in the absence of a resistance, well, up or down. And we know that free fall acceleration has a certain magnitude, about 9.8 or 10 meters per second squared. And it's a vector. It points down, straight down, because it's a vector. As any vector, it has components. And the question is about the x component of this vector. So if you chose the answer number 1, please raise your hand. Thank you. If you chose the answer number 2, please raise your hand. Thank you. Number 3. Well, the majority here was right. So first of all, actually, it is kind of instructive to see at all different options. Let's say the vector points like this, slightly to the left. In this situation, it should have 2 components, down and to the left. Let's say the vector is tilted slightly to the right. In this case, it has 2 components, down and to the right. If it's not tilted at all, there is no horizontal component. And of course, if we try to draw components according to our method, that will be the y component. And we can see that the y component is just equal to the vector itself. And this is just a dot. It's not a segment. It has no length. So there is no horizontal component here. And another way to prove it, well, we know that according to a definition of components, if we add components, we should get the original vector. But in our case, the original vector and the y component are equal. So a minus a equals ax, and that gives 0. So another proof, no matter what we do, we get the same result. A vertical vector doesn't have a horizontal component. That's it. And now we can use this fact for a mathematical description of a projectile motion. So relative to vertical axis, relative to y-axis, we should have a standard motion with constant acceleration. It's constant, not 0. So velocity equation, motion equation on the next slide. But simultaneously, the same object travels horizontally with no acceleration. No acceleration means velocity is constant. So horizontally, it travels with a constant velocity. What does it mean, vertically, horizontally? Well, we can imagine that we have a set of lights, very, very bright lights. Bulbs, 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 bulbs. So in that case, we can look at the motion of the shadow. And that shadow will be moving up or down with constant acceleration, like a free fall object. If we place a set of lights above the projectile and we look at the motion of the shadow on the ground, that shadow will be traveling with constant velocity. That's what it is. And all we need to do is to describe the motion of those shadows, all components. Yeah. And of course, for the motion with constant velocity, the motion equation is linear. The velocity equation is just not, it is not even an equation. It just says that the x component is constant. And for the vertical motion, we have standard equation, how velocity changes, how height changes. We just need to remember these numbers. These numbers. This number is equal to -10 if we choose y-axis upward. Same equations, but without extra terms, which are equal to 0. And here we explicitly show that axis points up, y-axis points up, and acceleration equals -g. And the last thing, mathematical thing to remember is a vector and components always form a right triangle. So this is a vector which represents the launch velocity, initial velocity. It could have been horizontal, vertical. For the vertical would have been just free fall. In general, well, it's tilted at a certain angle. So this picture tells us how to relate the actual initial speed and these numbers which describe horizontal motion, the x component of initial velocity, and this number which describes the vertical motion, the y component of initial velocity, pure geometry. And now we know everything about projectile motion. It's just a combination of two one-dimensional motions. One is motion with constant acceleration. Second is motion with constant velocity. Velocity, that's one thing we have to talk about. Instantaneous velocity. How does it look like? Well, so let's say we launched a ball. It flies like this. We can prove it's a parabola, actually. So if we wait a certain amount of time, the ball will be somewhere here. How can we describe its position? Well, we can use the position vector, r initial, r final. This is a displacement vector, delta r. Well, displacement vector has components, delta x, delta y. Delta x over delta t, what should it be? That should be velocity. But for the long period of time, that should be average velocity. And it should be only relative to x-axis. Delta y over delta t. That should be the y component of the average velocity. And now if we want to get to the instantaneous, well, these equations, which we could have used, but we don't need them. All we need is an understanding what instantaneous means. It means we have to consider two locations of the ball which are so close, so practically indistinguishable. So this is what we're doing. Displacement for the average velocity, then we make the time interval shorter and shorter and shorter and shorter, and we look at what is happening to the displacement vector, shorter, shorter, and we can see in the end that this vector, this arrow, should touch the trajectory only at one location, only at one point. So how do we call it? Tangent, tangential. And this is instantaneous displacement over tiny time interval. That's what instantaneous velocity is. And of course, as we know, if we take a vector divided by a number time, it might change the magnitude, but it does not change the direction. So instantaneous velocity always tangent to trajectory. That's a very important rule. We're going to use it in the future more than once. That's the rule. It works for any trajectory, not just for a projectile, or any type of motion. when object travels in space, the instantaneous velocity always tangent to trajectory at the location of an object. For example, if an object is here and now, instantaneous velocity here and now will point like this. That's it. This rule tells us how to draw instantaneous velocity of an object, any object, in any motion, and we will use it very soon, right now. Please think it through and tell me what you think. So in general, a projectile travels up and down, so there is always maximum height it reaches at that location, at the location of the maximum height. What can you say about the y component of instantaneous velocity of the projectile? Of course, you read, and you close your eyes, imagine, and you open your eyes back and draw. Then you look at what you've drawn, and you make a conclusion. So what's your conclusion? What's your answer? So before the ball reaches maximum height, instantaneous velocity points like this, slightly up. After, it should point like this. So at the highest location, it cannot point up, it cannot point down, it only can point horizontally. That's the first step. If it points horizontally, that's a horizontal vector. As we know already, vertical vector doesn't have horizontal component, so horizontal vector doesn't have a vertical component. That's why we call it horizontal. Of course, we could apply our method to search for components. That would be, well, that's velocity at the top, and that should be the x component of velocity at the top. And we can see they're identical, the same thing. And the y component doesn't exist, because if we draw both lines from both ends of a vector, it's going to be the same line, crosses at the same point. There's no distance, 0. So this is a very important fact we have to remember. At the highest point of the trajectory of the projector, velocity is not 0. It's not 0, it still travels. But the y component of velocity is 0. Done with theory. What's left? Practice. So this is a standard situation when the landing height is equal to the initial height. It doesn't have to be table to table. It could have been, I don't know, mountain to mountain. Doesn't really matter, as long as the initial and final height the same. That's the same problem. In this situation, we know the initial speed, and we know the launch angle. So this angle is equal to 40 degrees, and the magnitude of this velocity, which is speed, is equals 22 meters per second. And as we know, for the horizontal part of the motion of a projectile, we can write an equation for the motion with constant velocity. That's it, nothing else. For the vertical part of the motion, we can write two equations. The velocity equation well, positive direction of the vertical axis is up, so acceleration is negative g. And the motion equation for the vertical coordinate well, this step doesn't require thinking. It requires knowing and applying. There's nothing to think about. It's a projectile motion. There's a horizontal, there's vertical part. For the horizontal motion with constant velocity, for the vertical motion with constant acceleration, that's it. Of course, we can make it simpler depending on our choice of origin. This is 0. This is 0. Now, this is y final 0. What else can we write down? Well, the velocity triangle relates initial speed and two components. That's pure geometry. So we can immediately write Vx should be equal to 22 times cosine of 40. Vy initial should be equal to 22 times the sine of 40. Now, I don't have to write a subscript like initial or 0 for x component because it remains constant, it's the same. But when I'm calculating the vertical component of velocity, I have to indicate that I'm calculating here the initial value because in time it changes. When the projectile launched up, vertical component of velocity decreases to 0 and then like a free fall increases again. So this actually has been calculated, and one component is about 17, second is about 14. Now, what can we find? Well, the short answer, everything. For example, this distance from the location where the projectile was launched to the landing point has a name. We call it the range. And of course, the range is just equal to, well, the x coordinate of the ball over the whole flight. So this is 0. This is, well, about 17 times total time. Well, that's all we can do for now because we don't know the total time. But we actually can calculate the total time pretty quickly. What do we know about this location? It's a very specific location. When it lands, the final y coordinate is equal to 0. So we can ask, can we use this information? We can try. What does it mean, use? Well, it means write the motion equation and plug in everything we know. For the final location, that should be 0. This has been set to 0 by the choice of the origin. The y component of the initial velocity equals 14. This is supposed to be total time, minus 1/2 times 10 times total time squared. If we look at this equation, it has only one unknown, so it's a quadratic equation. We can solve it, but in this particular case, this is actually a very simple quadratic equation. We can easily simplify it. And that's what we should do every time. We write an equation, and without any thinking, we ask, can we make it simpler? Yes, we can. So we have to do it. That's it. How can we make it simpler? Well, first of all, we can rewrite it. 0 equals 14 times minus 5 times And now t, the variable here, is a common factor. We can cancel it out. So we can take the whole equation, divide by the unknown. What's left? 0 equals 14 minus 5 times time. And that gives us total time. Total, that's it, times 14 over 5 times 2, 2.8. Now, if you look at the picture, you can see the symmetry. Nature doesn't care about how we look at it. So we can look at like we'll do it now, or we can hide behind the screen and look at from behind, or we can imagine that the same ball was launched here and flies there. Symmetry. And that symmetry tells us that the time to reach the highest point, the time to get from here to here, what we call time up, and the time to get from here to here, which we call time down, should be equal to each other. We can prove it mathematically very easily. We can calculate each time independently. But at this point, we can just use this as a fact, which means total time total, should be twice of time up or twice of time down, which means time up or time down should be equal to a half of total, which is 1.4 seconds. Well, that symmetry is not always the case. It only applied when the final height of the projectile is equal to the initial height. If it's not the case, there is no symmetry. If we launch the ball higher and then it falls lower, so it takes less time to reach the highest location, highest point, and then go back. All right. Well, now the range. Yeah, the range should be equal to 17 times total time, wherever it is. Bless you. Now, another important feature, variable, the maximum height. The maximum height is equal to the y coordinate at the highest point. So because it's y coordinate, we have to use the motion equation again. 14 times time minus 5 times time squared. This equation describes the instantaneous location of a ball above the ground at any instant. See, this height changes from 0 to maximum back to 0. When the ball is at its maximum, when the time is equal to the value we call time up. So if we replace these generic independent variables with a specific value, this should give us maximum height. So maximum height will be equal to 14 times, what is it, 1.4 minus 5 times 1.4 squared, wherever it is. That's the maximum height. What about velocity? Well, we didn't use velocity equation yet. We could have used it, for example, for calculating time up first. X, Y. We know that at the highest point, Vy top equals 0. The velocity at the highest point is not 0 again, but it is horizontal, so it has no vertical component. This is V top. Since we know this fact, we can use it. We just have to write the velocity equation. The velocity equation for the vertical component of velocity looks like this. It describes how vertical component of velocity changes in time, specifically at the highest point. This is supposed to be equal to 0, and that was equal to 14, and this is 10. So we can use the velocity equation to calculate time up. We get exactly the same number, of course, 1.4 seconds, which tells us a very important fact. There is no one single way to solve a problem. There are many different ways to solve the same problem. And you can just choose any path you like and just walk it through. If we know time up and we know that the landing point and the initial location at the same level, that immediately tells us that time down also has to be equal to 1.4 seconds. Symmetry. If we know time up and time down, we can say that total time will be equal to doubled of that, 2.8 seconds. So we can get the same numbers differently, which is always a good thing to do. Just make sure answers match, because if they don't, most probably we made a mistake somewhere. We have to find it out. Well, so I got slides with calculations and more accurate calculations here, because here acceleration was equal to 9.8, not 10. Well, please take a minute and draw a picture for this situation. That's the most important part, because the rest is just writing equations, motion equation for horizontal part of the motion, velocity equation and motion equation for vertical part of the motion, then throwing numbers in, and whatever math says, that's the answer. So here, when you read and imagining what's happening, you need a little bit to think, you know, just a little bit. After that, thinking is not required at all. Just enacting the steps, enacting the procedure, following the instructions. So what I read, I see a barn. So, well, probably everything is on the earth. We have to wait for Elon Musk. So there is a barn which is 6 meters high. And a guy shoots the ball. So the guy probably on the ground shoots the ball. When the ball is released, the ball is 2 meters above the ground. And, well, what should be happening? It should, well, again, yeah. Three-pointer. So it flies and it lands. There's initial velocity, which should point like this. And what we know about it, the x component of this equals 10 meters per second. Also, we know gravity equals negative 10 meters per second squared. And also we know the range from here to here, well, when it lands here, okay. From here to here, the range, the horizontal distance traveled by the ball before it hits the roof equals 20 meters. It doesn't matter actually what we know or don't, yeah. Because when we solve an equations, we don't look for specific values initially. We just try to connect everything we can with each other. Well, of course, now we would have to set the x and y axes, x, y. And we can choose the origin on the ground or at the initial location, doesn't really matter. Let's set it on the ground. So what does it tell us? It tells us that x initial equals 0 by our choice. X final equals 20 because we can read. Y initial equals 2. Y final equals 6. It lands on the roof. And, well, oh, this is a better picture. This is the maximum height. In this situation, time up is not equal to time down. But who cares? It doesn't affect the strategy. So, quickly, x equals Vx times time, hence. That's an arrow, hence. Well, again, this expression tells us the instantaneous x-coordinate at any instant. So the x-coordinate changes in time, and when it equals 20, the ball lands on the roof. This instant has a name, total time. In this problem, since we know the range and we know the x component, this equation actually immediately tells us total time. Now, where else? Well, y equals y initial plus plus 1/2 -10 times squared. Okay. This is a generic general equation for any instant, but now we actually can use it for the instant when the ball lands on the roof, because we know the total time. When it lands on the roof, the final y should be equal to 6. The initial y is equal to 2. We don't know this number. What do? We just skip it. Who cares, whatever, yeah? So 2 seconds, 1/2, -10, 2 seconds squared. No? No. We cannot skip it. We cannot leave an empty space in an equation. We have to write something. When we know a number, we write a number. When we don't know a number, what do we write? That's variable. But now if you look at this equation, that variable is only variable in that equation. So we can solve it and calculate y initial. And when we know these numbers, yeah, that's it. We can follow the strategy we used before. As long as we know the x component and the y component of velocity, we can solve the problem for every single thing. Well, you're going to be practicing today in the lab, tomorrow in the lab, but nothing else left, basically. That completes whole theory, that completes different examples when the initial height and final height equal, when the initial height and final height different. Nothing else left. Any questions, please? Well, now we're going to switch to a different topic. Remember this experiment, very complicated one. We know from that experiment that motion is relative, and every time when we talk about motion, we have to say specifically relative to what. But sometimes an object relative to which we consider motion also is moving relative to something else. Like in this example, a passenger is moving relative to the airplane, but airplane is moving relative to ground. And this is just one of many possible examples. That could have been a cruise ship or a boat which travels in a river, which flows relative to shore. So we need to understand how can we describe this type of the motion. And first, we start from situation when everything is moving linearly in the same direction or opposite. So I'm going to switch to the camera. All right. So this is a motorized car which represents anything moving. This looks like it's dying. Okay, this is live. So this is the initial location of this cart relative to whatever it is, airplane, cruise, river. And this is the initial location of this cart relative to the ground. So when, well, technically what we have here is three different objects. We can call them 1, 2, 3. Well, we can call the ground number 1. This, wherever it is, number 2. And the cart will be number 3. So the physical nature of these objects does not matter, absolutely. We can call them cart, paper, table, or just 1, 2, 3. And this is the displacement of the object number 3 relative to the object number 2. And we see when the object number 2 is at rest relative to the object number 1, the displacement of the object number 3 relative to the object number 1 is equal to the displacement of the object number 3 relative to the object number 2. And you should be able to say exactly what I said. So practice. What's going to happen if the object number 2, let's say river or airplane, moves relative to the object number 1? Fact number 1, the displacement of the object number 3 relative to the object number 2 is the same, of course. That's only between these two. Whatever happening around does not matter. However, now the displacement of the object number 3 relative to the object number 1 is different. How different? This is how. That was the displacement in the first place when the second object was not moving. And now, and now what we can see is this is the displacement of the second object relative to the first. This is the displacement of the third object relative to the second. And this is the displacement of the third object relative to the first. And it equals to the sum of these two displacements. So how do we call it? Well, delta R of a second relative to the first. Delta R of the third relative to the second. And this is delta R of the third relative to the first. We don't need it anymore. We can write an equation, delta R of the third relative to the second. We can write an equation that the displacement of the third object relative to the first is equal to the displacement of the third object relative to the second plus the displacement of the second object relative to the first. We can say it in words. Let's say it's a boat, river, shore. The displacement of the boat relative to the shore should be equal to the displacement of the boat relative to the river plus the displacement of the river relative to the shore. By the way, it doesn't really matter what you call number 1 object, number 2, number 3. For example, you want to call this number 2 and this number 3, and that will be number 1. It doesn't change this equation. But this equation, this specific equation, will sound differently. For example, the displacement of, what did I say? 2, 3. I forgot how I numbered them. All right, doesn't matter. The displacement, let's say, of the ground relative to the boat should be equal to the displacement of the ground relative to the river plus the displacement of the river relative to the boat. Or the displacement of the river relative to the ground should be equal to the displacement of the river relative to the boat plus the displacement of the boat relative to the ground. And we can keep going and going and going. You can see what's happening every time. If this is the object number 3, this is the object number 1, we kind of insert the object number 2 in between and automatically get the correct equation. We just have to remember a displacement is a vector. So this is just one possible example. But from this one possible example, we've extracted equation which works for any possible situation, for every possible situation, as long as we have 3 objects moving relative to each other. The displacement of the third object relative to the first will be equal to the sum of 2 displacements, third relative to the second plus second relative to the first. But more importantly, as we know very well, displacement over time is velocity. So this is how we relate velocities of objects when they travel relative to each other. For any 3 objects, the velocity of the third object relative to the first is equal to the velocity of the third object relative to the second plus the velocity of the second object relative to the first. This equation does not depend on the nature of the objects. Airplane, cloud, ground, boat, river, shore. Doesn't matter. In this example, this is a passenger, ground, and airplane. The velocity of the passenger relative to the ground is equal to the velocity of the passenger relative to the plane, plus the velocity of the plane relative to the ground. But each velocity is a vector, it's an arrow. So in order to use this equation correctly, we need to know how to add vectors. If we don't know how to add vectors, we might make a mistake when applying this rule to a specific situation. Well, this equation has a name. The law of relative velocities. Yeah. And now you know everything about relative motion. No extra theory. Just practice. I'm going to start this problem, but I'll finish it tomorrow. So what's happening? An airplane makes a round trip. So it flies east and then flies back. And each way it travels 112 kilometers. The pilot observes the cloud and measures the speed relative to the cloud. And the speed relative to the cloud means the speed relative to the wind, the speed relative to the flowing air. But that air also travels 20 meters per second relative to the ground. So that's what we know. So this problem has two parts, right? At first, the guy flies to the right. East for us is to the right. So that's the distance traveled. So this number represents the speed of the airplane relative to wind. Thank you. Well, thank you very much. So I'll pick up tomorrow from this. Do more examples on relative motion. And tomorrow we should start forces. And the rest of the week will be designated to study forces. All right. You have to send me an email about that. Hmm? Again, see, you need to put your words in writing. Send me an email with everything you just said. Yes. Well, we've changed office hours. New schedule. Someone has to be there today from 10 to like 3 or 4. And look it up on Blackboard, I think it's updated. Or you can look up on the board by the